Hello. On behalf of Cephas Armstrong Mensa, David Henderson, Joseph Michaels, Jason Rice, Nelson Tran, and myself, Gary Morris, we are Group 9, and our presentation is on software maintenance.
My name is Cephas, and over the next couple minutes, I'll be continuing the conversation of what is for software maintenance, which is a process for changing a system after it has been delivered. There are three main types of software maintenance, but I'll be covering parts of what is known as environmental adaptation. EA is maintenance external to the software, such as maintenance at the operating system, supporting software, or at the hardware level. EA accounts for 18% of all maintenance activities, as reported by Somerville. Hardware EA is maintenance to support a hardware change in the system, because improved hardware can support new features or standards, such as using more RAM or architecture. Hardware changes present some of the more specific problems when it comes to software or maintenance enhancements, as noted in what you can term as code decay. That is when the software becomes more difficult to change due to time, cost, or quality. Over the next minute, I'll be leaving with some examples just to get your mind around the concept of what hardware upgrades are. Such can be from when we shifted over the last decade from 32-bit to 64-bit support to use more RAM or processing power. That meant when that standard came available at a hardware level, operating system and application developers had to go back to rewrite software to be able to support the new features that was promoted by the 64 bits. Network interface cards as well, when it shifted from 10 to 100 to 1000 megabits per second speeds, protocols had to be revamped and software had to be rewritten, drivers to support the speeds that the hardware was promoting. Bias to UEFI is another feature that has happened over the last couple of years. That allows us to use up 2 terabytes or greater hard drives at the operating system level. Lastly, TPM chip is something that also happened over the last decade or so. That gives us encryption and security also at a hardware level. When that happened, software had to be rewritten to support such security measures.
Hello, my name is Joe Michaels, and today I am discussing design errors in maintenance. First off, let's define what a design error is. After a bit of research, I came across a paper by Joachim Primer. In it, he says design flaws or code smells are program properties that point out a potential flaw in the design of a software system. Now, these flaws lie in the foundations of the development process, making them difficult to find and expensive to fix, often due to late testing of the system. So, what are poor design practices? Well, a few years back, a list of both good and bad practices was created as a sort of litmus test to help a designer or developer determine where their code stood. The poor practices, now called anti-patterns, provide a list of the most extreme examples to avoid. Now, I have visually provided several practices which you can look at. Some others not listed include the golden hammer and input clutch. The golden hammer is when a developer or architect discovers a great solution and attempts to apply it to every problem due to an unwillingness to learn to apply a different, better suited solution. Input clutch is when the developer allows the user unbridled input access to their software. The lack of validation allows for illegal character entry, leading to possible security breaches from injection attacks. So, how do we prevent these issues from arising, and how do we fix them when they do? Well, as previously mentioned, the further along the cost of change curve that an issue is discovered, the more expensive it will be to rectify. Common practices include utilizing test-driven development and continuous integration, that is to say, become more agile. Also, make sure to refactor your software when given a chance. Unfortunately, this is a great example of an efficiency process, as most businesses don't see the return on value from refactoring an old solution as long as it continues to work as is. Because most of the life of the software project will exist in the maintenance phase, throw more at the upfront cost of properly designing the system to save even more in the long-term maintenance. This will reduce future issues and delay the need for major refactoring.
Coding errors are bugs introduced during the implementation of an application. These are accidental mistakes causing unintentional things to happen within the application. Some types of coding errors include syntactic errors, null pointers, and indexing errors. One example of a coding error is a calculation for an auto loan percentage. Instead of typing 1.10 for the APR percentage, the developer put 11.0. This would cause a person to get charged more each month, making an unhappy customer. So how are coding errors discovered? Well, an obvious way is through its use. Sometimes it may be hard to tell you actually have an error until functionality is put to the test in a real-world situation. Best case would be through quality assurance practices catching the error before application release. Other methods of discovery include static analysis, which tests code for possible errors without needing to run the code, and automated testing, which makes use of test cases, mainly testing if the submitted code messed up any previously submitted code. Coding errors are fairly cheap. They usually don't take much time or effort to fix, but they can have big implications on an application. A large amount of application failures are from coding errors. One example of a major result from a coding error is the Patriot missile defense system failure, which because of a rounding error in the code, ultimately failed to stop an enemy attack. Although we cannot prevent all possible coding errors from occurring, there are some things that can be done to minimize the chance of a coding error. Making use of static analysis tools, perform quality assurance testing, and use of test-driven development techniques can help by testing functionality of an application. Then, pair programming and code reviews can help by getting more eyes on your code, getting more perspectives, and potentially preventing a coding error from happening. Finally, when a coding error is found, if it affects critical systems, it should be handled in a timely manner to maintain the application.
Hi, my name is Nelson, and I will be talking about managing changes in system requirements. To review, system requirements are the requirements that describe the functions of a system that, when fulfilled, satisfy the needs and requirements of the stakeholders. In other words, system requirements describe how to build a system that satisfies the business requirements of the project. System requirements must be properly elicited from stakeholders, and like other types of requirements, system requirements may change over the course of a software project, perhaps because of increased understanding and experience of the stakeholders during the project. A large part of companies experience requirements variability often. Only in a few companies are requirements stable for the entire project. So it is important for project managers to be able to effectively manage requirements to prevent stakeholder expectations from spiraling out of control. So how can a project manager manage system requirements effectively? One way is to structure a software project so that deliverables can be delivered iteratively and incrementally. Agile development is a great methodology for managing system requirements, since the core of the Agile philosophy is to provide a set of values and principles for software development that allow teams to manage volatile requirements. With frequent incremental deliverables, it is much easier to get feedback from stakeholders and to identify anomalies in the software product versus what the system requirements intended, and to respond to those anomalies appropriately, whether that means adapting to new system requirements or to make sure that the software product validates against the system requirements. Along those lines, it is important to trace software design back to the system requirements. Effective requirements management allows project managers to manage the scope of a project and more easily adapt to the unexpected changes in requirements. By enforcing good documentation, it also provides good visibility into the software system itself, since every part of the software product should be traceable back to the system requirements.
Software functionality is added after a requirements elicitation has occurred by one of two ways. Nelson talked about changes to system requirements, but requirements can also change through fluctuating business requirements. My name is David Henderson, and I'm going to talk about functionality addition through business requirement changes. Business requirement changes are, as the name implies, business requirements or features being added or changing after the requirements and design have already been finalized. They can happen as casually as in around the water cooler, hey, do you know what would be cool? From the boss, or formally such as through a requirements elicitation meeting. This isn't restricted to new features, unfortunately, so these business requirements changes can occur at any stage of software development. These changes can therefore be expensive and can delay any project. Designing the software to be modular can prevent sweeping changes to a project. Prevention is the best approach. It won't be a problem if it doesn't happen. Thorough requirements elicitation can reveal requirements that are hidden but may appear later. The aim is to hopefully cut down on the more casual email chains of, oh, another thing I thought that would be cool. However, a developer can only do so much elicitation to solidify what the requirements are, but the problem is that sometimes the unknown and new problems are actually the least threatening. Existing, finalized business rules can change, and dependencies may need changing as well, which can detrimentally cascade. To guard against this, developers should make the project modular so that new modules can be added or existing modules can be changed without much effect elsewhere. Agile is developed to be more responsive to change, and changes to business requirements are able to be mitigated. Agile can put the requirements on a backlog and rank its priority accordingly. This approach is the most effective because the prior two are still preventative, and despite best efforts, requirements will still change. This provides the leeway of adding new features with the offset of allowing programmers to decide which iteration they are going to implement it in. Regardless of how business requirements changes are handled, they need to be considered and handled to prevent projects going awry and becoming bloated and mismanaged.